Our topic today is QAM Demodulator. So, quadrature amplitude modulation. QAM is stand for quadrature amplitude modulation. So we will see the demodulator at block level today, and we will see how each block, how each branch processes the received signal. So before going to the block diagram, let me recall the mathematical expression for our QAM modulated signal, and we said in our previous lecture that we can represent the waveform Si of t, a QA quadrature amplitude modulated waveform, as AI P of t and cos of 2 pi fct plus theta I. So this is the representation of a QAM modulated signal. You can see that each signal, or each you can say each symbol Si of t can be, each symbol Si of t has a unique pair of amplitude and phase. So both the amplitude and phase Ai, for each Si of t you have a unique pair of Ai and theta I, right? So this pair, this unique pair, this is unique for each Si. This is unique for each Si, and this is how different received symbols are differentiated from one another. So we also derive this expression for our signal waveform, and that this mathematical form can also be rewritten as S sub I1 psi 1 of t plus S sub I2 psi 2 of t. So this is how we represent our signal waveform as a linear combination of these orthonormal basis functions, right? So I hope you are familiar with these functions now, and you are familiar that your psi 1 of t is actually under root 2 over t cos 2 pi fct, and psi 2 of t is minus 2 over t sine 2 pi fct, right? So these are our orthonormal basis functions, and we said that these we can represent each symbol, each QAM symbol, or each QAM signal waveform as a linear combination of psi 1 and psi 2. And in the vector form, we can represent Si of t in the vector form by just these Si sub I1 and S sub I2. And these S sub I1 and S sub I2, these are actually these are real numbers. These are real numbers. So we will see that in the for each symbol, you have this pair is unique, which distinguishes that symbol from other symbols in the M array digital modulation scheme or in M-array QAM scheme. So you are familiar with the value of m, that your m actually is 2 raised to the power k, and k is 1, 2 and so on, right? So your m, the possible values of m are 2, 4, 8 and so on. So when we say MQM, when we say MQAM, M-array quadrature amplitude modulated signal, this M represent the number of unique signal points used for transmission, the number of unique symbols or signal points of that constellation, signal constellation. So we will use this is what we learned earlier. We will use this form to discuss our demodulator, this form, right, which is an easier form, and the demodulator, from here we can see that our modulator, we discussed modulator in details in the previous slide. It's just for the purpose of recalling, because we at the demodulator we have to detect that signal, the signal which we receive from the modulator or which we receive from the transmitter, that should be processed. So we receive this signal from the transmitter side. Ideally, we are assuming an ideal situation. We say that there is no noise and no channel effects. So the channel is assumed to be ideal, and we are discussing our demodulator at block level. We will discuss it right now at block level in the absence of noise, and we will see how the signal can be detected. Now keep in mind this form. Let me bring it to the center of the screen. This form which we saw earlier, this form actually shows that our signal is two-dimensional, right? It is two-dimensional. So our signal constellation our signal points would lie in this two-dimensional Euclidean space. So it can be these points which we discussed in our last lecture. So any of these points, these are just for M16, when we have 16 points, or square QAM constellation. So we can see that each of these points has two coordinates, one x-axis, one represent along psi1 axis. Psi1 axis is psi1 axis, and we have a psi2 axis. So two coordinates are there, and we will try to detect these two. Actually, we will try to detect these two parts at the QAM demodulator. So let's see the QAM demodulator at block level, how it would look like. Suppose we are now here we assume we would like to write our received signal, which is in this form: SI1 psi1 of t plus SI2 psi2 of t. And as you are familiar, this SI1 and SI2, S sub I1, S sub I2, these are actually the images of the signal over psi1 and psi2 respectively. So let's see the demodulator at block level, how the simple demodulator would look like. So if you want to draw your demodulator, it would look like you would have a received signal, right? And of course you have two orthonormal it's a two-dimensional signal, so you would have two branches. An upper branch, this would be your received signal. We assume that we receive the same signal which we transmit from the transmitting end. Then you have a lower. Let me draw this modulator at block level, and then we will discuss each and every block, and the input and output of each block. So we would have a carrier recovery block here, a carrier recovery block CR, and from this carrier recovery we should have some signal of this form, 2/T cos of 2 pi FCT. In the upper branch, similarly, we would expect that our carrier recovery branch can give us another signal which is minus 2/T sine of square root minus 2/T sine of 2 pi FCT, right? So we expect that our carrier recovery branch can give us these signals. It recover the perfectly synchronized carrier. We get a perfectly synchronized carrier from the CR block, and we can just have this phase shifter for the lower branch where this, and we have in the upper branch cos of 2 pi FCT, right? Now here we have an integrator. And the integrator should integrate this input, right? It would integrate it, and we will get an output which is we can say it is R1K. Similarly, we would have an integrator here. And the output of the integrator, we say it is R2K. So we have R1K in the upper branch and R2K in the lower branch, and then we will give this R1K and R2K to another block, which should compute the length Li. Right? And it would choose it would compute this length Li. Actually, it is to detect the symbol. Now, how the Li, or let me give you this a little bit explanation here in this diagram. If you see here, now if you see each symbol has each signal point has a length. For example, if this is the point, then the length of the vector is this one, and this length of this vector depends upon the length of each vector depends upon the coordinates, right? And each of these points has a unique length. Now, our demodulator would get two values from the output of the integrator from the upper branch, and one at the output of the integrator from the lower branch, and then it would compute the length, and that length would be, because that length would be compared with any of these. So it would choose the one that has the same length. If this L equals this one, it would say that okay, the symbol is detected. If it is this one, it would say this symbol is it is this symbol. So the detection would be based on actually these X and Y points, and each you can say this, the point which is along X axis, along horizontal axis, along Y, along the point along the vertical axis. So this would detect our signal, right? This would detect our signal. Now if you see the block diagram, or let me further simplify it. If you see the block diagram, let me erase this last block. Suppose we are just based on this one, these two outputs, R1K and R2K. Based on these two outputs, R1K and R2K, we say that we can identify our symbol. We can identify our symbol, right? So if it is plus in the because we are now processing it in the absence of noise. So up to here it would be okay. So let's try this demodulator. Let's see whether we can get the received signal, perfectly or not. We can okay. We would expect that our now what we would expect if we are getting R of t at the receiving side, we would expect that our R1K should be equal to SI1 and our R2K should be equal to SI2, because if we get here SI1 and here SI2, it means we can reconstruct, we can find that we can easily detect our signal correctly. So this is what our demodulator should give us. This is how the demodulator should give us these outputs, right? This is what we expect from our demodulator. So let's try this one. Suppose we have R of t at the input. And this R of t in the upper, let me concentrate on the upper branch, then I'll come to the lower branch. If we go to the upper branch, now the signal over here, which is the input to the integrator, we need to find this signal. Let me write equation for this signal. If you see, this signal is actually the product of R of t and cos of 2 pi fct. So we have, let me say this is point A. So at point A, we have a signal which is the product of R of t multiplied by 2 over t cos 2 pi fct. And if we solve this one, what do we get? This is the signal at point A is actually what is this? If you see, this is psi 1 of t. This is actually psi 1 of t. So actually we have R of t, which is SI1 psi 1 of t plus SI2 sub I2 psi 2 of t, and it is multiplied with psi 1 of t. Right? It is multiplied with psi 1 of t. So if we find this product, this is actually psi 1 of s sub I1 psi 1 square t plus s sub I2 psi 1 of t psi 2 of t. This is at point A. This is the signal at point A, right? This is the signal at point A, or you can say the input at the input of the integrator. Now the integrator has to integrate this signal, and if we try to find out the output of the integrator, the output of the integrator would be now let me represent it. Let me say this is my signal I, or let me say this is my you can give it any name. Let's give it some name here. Suppose this is the signal A of t, right? The signal at point A is A of t. So A of t has to be integrated now to get R1k, right? So this is the signal A. This is the signal A of t. This has to be integrated to. So if we want to find out R1k is actually the integral of A of t dt, and the integral is between 0 to t. For each time interval, we have to take this integral. We want our integration for this time interval. So in the first time interval, we received R of t. If we integrate it, we would get R1k, which is the integral of A of t, and A of t is actually s sub I1 psi 1 square t plus s sub I2 psi 1 of t psi 2 of t and dt. So this is the output of the integrator. The output of the integrator. Now we can have two integrals, this one and this one. So let's split it into two integrals. We have 0 to t s I1 psi 1 square t dt plus 0 to t s I2 psi 1 t psi 2 t and dt. Now if you solve it further, you would get R1k, which is now SI1, as I said earlier, that these are real values, real numbers, you can say, SI1. So we can write it outside this integral, and we will have psi 1 square t dt. Similarly, we can write SI2 outside this integration, and we would say psi 1 t psi 2 t dt, right? Now what is this? I hope you are now familiar with this from your previous knowledge. You are familiar with this is actually the energy of psi 1, and the energy, because this is orthonormal basis function, as we discussed earlier. Our psi 1 is orthonormal basis function, so this integral would give you 1. So what do you get here? You actually get SI1, and this is 1 unity, so I'll just skip it. you get SI1, and from here SI2. Now concentrate over this one. The Psi1 and Psi2, these are orthonormal basis functions. So these two are orthogonal. And if the two signals are orthogonal, their dot product, which is defined by this integral, their dot product is 0. You can verify this. So here you would get 0. And you can see very easy. Now I am leaving it this verification for to the end. We can see that this product is actually 0. So what do you get? In the upper branch, you get R1k, which is actually equal to SI1. And this is what we were expecting from our demodulator, that we should get from the upper branch we should get SI1, right? Now let's concentrate on the lower branch. Let me go back to the block diagram. So we concentrate on the lower branch. If you observe the lower branch, now here you can see your signal in the lower branch. What happens to our signal? Our signal comes here. It is multiplied with this one. Now here, this is multiplication. And what is this? This is your side 2 of t, right? It's multiplied here, and at point B, suppose this is point B, you would get B of t, which is the input to this integrator. So let's try to find out B of t first. It is multiplied with psi 2 of t. Now if we go to our signal, if we go back and we try to find out B of t. Now we are interested to find out B of t, the signal at point B. B of t, which is the received signal multiplied by psi 2 of t, right? So this is the received signal. Now you can rewrite it. Your received signal is S sub I1 psi 1 of t plus S sub I2 psi 2 of t. This is the received signal, and you are multiplying it with psi 2 of t. When you multiply this with psi 2 of t, what do you get? You get B of t, the signal at point B, which is SI1